last year, you guys remember I did I did this graphic organizer piece. Do you remember this? You guys remember this? Okay. Test-wise, one of the most influential pieces was what we're going to do today. Okay, you guys will be excellent at this. I have no doubt. This is one of the most fundamental parts of calculus. So when you guys leave calculus, chain rule is a pretty big thing. Got to be able to do it, right? Got to be able to do f of x plus h minus f of x all over h. Got to be able to do it. Limit as h goes 0. Have to do that. This, huge. If you walk away from Calculus 1, you can't do this stuff, your professors will say, well, you obviously never took Calculus 1. Okay? This is prime to what we need to know. Okay? So, central. So, you're going to want a picture in your mind, and there's lots of different pictures we could draw with these. You have to look at the definition. So we're going to look at a first derivative test and what the first derivative tells us. The first derivative can tell us if something's increasing. And that is if the derivative is what? Above 0. If it's greater than 0, then the function is increasing. The function is decreasing if f prime is... If there is a local max or a min, if there is one, then f prime of x is equal to 0. That doesn't mean that just because you take the derivative and you get 0 that there will be a local max or min. It does mean that there is, in fact, if there is a local max or min, then this is true. Okay? So we have those pieces. Now, what I help people do is kind of, again, try to organize their information. And the reason why I did this is because people got confused with this in the years past. So up top here, I simply write f prime of x. And that's my derivative number testing line. And it's going to match with my graph right here. So, what's that? Yeah, if I take the derivative. And so you tell me right now, is f prime of x positive or negative right here? Positive. How about here? Okay? And so I can mark that spot, right here. The derivative is 0. It's positive before that. What happens after that? So I can put that spot up here, I'll mark it. It's negative in between. And then after that? Okay. Now, I know that you already understand that piece, but now we're going to look at a second derivative test. So that's what the first derivative can tell us. The second derivative tells us something that's really, really cool. And it tells us about concavity. Concavity is the general shape of the graph. Okay? And some people try to think of concavity like this. Is it going to hold water or is it going to dump out water? So like right now, if you filled this part of the graph with water, would it dump it out or would it hold it in? Dump it out, and so it's like you're tipping the cup upside down. Whereas this part, you're holding it in. Okay? So we would say that this is concave up, this section here, and that this section is concave down. So the way we define it, though, is kind of interesting. Okay? Derivative positive or negative? The second derivative is going to be the rate of change of the first derivative, right? The first derivative is the rate of change of the original function. The second derivative is the rate of change of the derivative. So you tell me, if my pen models the slope of the function at that point, you tell me, is the slope becoming greater or smaller as I move along here? See how the tip of the pen is dipping down as I move? that means that the derivative, the second derivative, is negative. Look at it again, okay? The tip dips down until, oh, all of a sudden here it starts to head back up, right? There's a special spot there where the derivative stops, the tip of the derivative stops dropping down and it starts tilting back up. Question. Exactly. Yep. If you graphed it, so if you graphed the parabola that would model this, you would see that the parabola would turn from negative to then positive. Exactly. We call this concavity, and we define it as this. It's concave up if f double prime of x is greater than 0. It's concave down if f double prime of x is less than 0. If there's an inflection point that exists, it exists when f double prime of x is equal to 0. The inflection point is where it changes concavity. We'll show you right now the inflection point on here. So as you look at my pen, again, you can see the tip of the pen is dropping until I get to right about there. The tip is still pointing down, isn't it? But it's starting to get pulled back up. So here it's dropping, 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 and now it's getting pulled back up. So it's this point right about here that we call the inflection point. No. And so we say that this is the portion that's concave down. This is the portion that's concave up. Why? Because if you do the second derivative test and you put your f double prime of x here, we say that f double prime of x is going to have a value of 0 right there. And again, is f double prime or is it positive or negative here? It's negative. It's 0 right here, and then it's positive after that. When we try a couple examples, trust me, you guys will get it. You'll get it great. This will take us a couple days to work through. We want to, you want to be excellent at this. We don't want to fly by this, okay? Let me help connect your understanding a little bit here, okay? What degree function is this? First, second, third, fourth? Looks like a third degree function. So how many times should it cross the x-axis? 3. We have 3 spots where it's going to cross the x-axis as long as all the solutions are real, okay? So if I take the derivative, it reduces from a first degree down to a second degree. So how many points should I have where it has a local max or local min? 1, 2. If I take the derivative of a second degree, I get a first degree. So how many inflection points should it have? 1. Okay? And so you can see the parts that you have here in play. Now, here's the last piece that we have to identify. Okay, before we just knew that if you take the derivative and set it equal to 0, there's a good chance it's a local max or local min. But we didn't know which it was. We didn't know if it was a local max or if it was a local min. Well, we can figure that out right now. Look at your graph, okay? Is this a local max or local min? It's a max. Is the second derivative positive or negative? The second derivative is negative. So if it's concave down, it has to be a local max. If it's concave up, it has to be a local min. So how do we test to see whether or not it's a local max? If f double prime of x is negative, then it's a local max. If f double prime of x is positive, it's a local min. And that gives us the information we need to know. What do you think? Let's put it all to work. Let's see if we can get through, we'll for sure get through one, maybe two problems here. Okay, for the following functions, identify intervals of increasing, decreasing, concave up, concave down. Also identify local max and min and inflection points. Okay. Okay, you are not going to have an accurate sketch of the curve today. That's not our goal, okay? You will be expected, so this is lesson 4.3. After we do 4.4 and 4.5, you will have to take the information that you get and produce an accurate sketch. So the cool thing is that you can walk away really from calculus and be very efficient with drawing excellent graphs. Now, right now, you say, well, I can plug into my graphing calculator. Again, put yourself in Isaac Newton's place. Isaac Newton wants to draw this graph, but if he's going to draw this graph, does he really want to plug in 100 points and make an X and Y table? No, and using calculus, we can get some really cool information really quickly. What does 1 over 3 x to the third minus 4x plus 2 look like, do you think? Yeah, it looks like kind of that shape, right? Okay, that's what I'm guessing, okay? Here's what we're going to do, okay? We're going to take the first derivative, okay? First derivative. What is f prime of x? Everybody agree, x squared minus 4? What is f double prime of x? Very good. So, watch what happens here, okay? I need to figure out where is 2x equal to 0? At 0, right? Okay. F double prime of x is equal to 0 here. Now I'm going to do some testing, okay? Let's plug in a negative value. What's a negative value, or what's the value to the left of 0 I can plug in? Negative 1. 2 times negative 1? Negative 2. That's a negative value. What's the value to the right of 0 I can plug in? 2. 2 times 2 is? That's positive. We have now decided already where the function has an inflection point. We've also decided that over this area the function is concave down. We've decided here it's concave up. Okay? Next thing we can do. Let's look at our first derivative. X squared minus 4. Where is the function equal to 0? Positive 2 and negative 2. Let's mark those on our number line. Okay? What's a point between negative 2 and positive 2 you can plug in? Let's plug it in. 0 squared minus 4 is negative 4. So the value is negative between here. What does that tell us about the function? It's decreasing. Very good. What's the number to the left of negative 2 you can plug in? Negative 3 squared is 9 minus 4, 5. So it's positive. That tells us the function is increasing. Okay? What's the number to the right of 2 I can plug in? 3 squared is 9 minus 4 is, that's positive. So again, the function is increasing there. Okay? So I don't have a lot of room here, but I really should have given you guys more room. My apologies. Let's just go right into here, okay? We'll make do with what we got today, okay? So I will draw a rough sketch here in a second, but let's rough sketch. Intervals of increasing. Can somebody tell me where this function is increasing? Very good. Negative infinity to negative 2. Hold on. Does anybody not see where we get that? Okay. The function is defined to be increasing when the first derivative is positive. The first derivative is positive from negative infinity to negative 2. The first derivative is also positive from 2 to infinity. Yep. Increasing and decreasing are always first derivative stuff. Decreasing. Negative 2 to 2. Concavity. Concave up, concave down. Where is it concave up? Which derivative do I look for that? Do I look at second derivative? Very good. From 0 to infinity. Concave down. Negative infinity to 0. Max. Min. Inflection. Local maxes and local mins happen where the first derivative is equal to 0. First derivative is equal to 0 at negative 2 and positive 2, we said. Okay? So you tell me, at negative 2, is that a local max or is it a local min? Why is it a max? Yeah, okay, so good. So you see, you're saying it's increasing, then it's decreasing. Good. The other way is that the second derivative is negative. That means it's concave down. So you can see second derivative is negative, concave down, just like so. And so you can see this point here. It's going to be concave down at negative 2. So we have a max. What is the y value for my max? How would I figure that out? I'll get back in. Negative 2 to the third. 8. 8 times 1/3. 8 thirds. Negative 2 times 4. 8. So obviously you got a positive 8 here, so plus 24 over 3. And then plus 6 over 3 if I turn them all to like fractions. Common denominators. 38 thirds. Let's look at our second spot where it's the derivative is equal to 0. That happens at 2. And is that going to be a local max or local min? Min, because it's concave up. So it's got to be a local min. So that happens at positive 2. How do I find the y value? Plug it back in. And if you plug in 2, you get 8 thirds. And now it's going to be oh, no, I'm sorry. Yeah, you guys are right. You guys are absolutely right. We had a negative 8 thirds plus 24 thirds plus 6 thirds. So negative 8 and 24 is 16 plus 6 is 22 thirds. Now if we plug in positive 2, we do get a positive 8 thirds minus 24 thirds plus 6 thirds. So that's negative 16 thirds plus 6 is negative 10 thirds. Your point of inflection happens at an x value of 0. Plug it in and you get 2. So here's all I'm going to do, okay, is you could draw a very generic sketch at this point. 22 thirds is like, what, 7 1/3? And negative 10 thirds is negative 3 1/3. So if I just, put a tick mark here of 5, negative 5, negative 5, positive 5, I can now make a fairly accurate sketch. Inflection point at 0,2, I'll put that spot there. A max at negative 2, 7 1/3, up there. Then 2 and negative 10 thirds and negative 3 1/3, about there. We don't know exactly where it crosses the x-axis because we didn't find that out. We could do that. Doesn't really factor very nicely, so it'd be pretty difficult. But that's our shape. And we found all the important information about it. Here's all I want you to do. Cross off D. I want you to try B on your own. The rest of the time, okay? You don't have any homework tonight. We're going to work more on this tomorrow. I want you to try B right now. You got 5 minutes. Let's see what we can do. Whoops, sorry about that. Whatever this is. I want you to do this one right here. Do this one right here. Okay, that's about what you should come up with. If you graph this, it's like if we call this 5, 1 second, negative 5, you can just plot some points here. Negative root of 2, 5.64, 0, 0, root of 2, negative 5.64. See the shape you get. So there you go.